Thank you, Suzanne, for this nice introduction. Also, I would like to thank Wouter and Mustafa to already introduce a bit the highlights of Safe by Design from product and process design, which we will see how these come together in the infrastructure. I hope you can see the presentation at least. My name is Vanhauten from ThinkWorks, and ThinkWorks is responsible for the development of the implementation of the infrastructure. And I hope in the next half hour to introduce you, based on an industrial example within our case, how the infrastructure can be used to support Safe by Design and Safe by Design strategies. Before I go to the live demo, I just first want to briefly introduce you on the case itself. It's one of our industrial case partners, Creative Nano, who use titanium dioxide nanoparticles in paints, and they apply them for their photocatalytic degradation properties. So basically, you can see here in the middle a schematic overview of the nanoparticle, which under light, normally under UV light, can create reactive oxygen species, and with these species, pollutants in the air are reduced. But of course, what our partner wanted to achieve is that this paint can also be used in an indoor scenario where less UV light is available. And in order to make that happen, sulfur doping was added to these particles in order to reduce the band gap. And that basically allowed these nanoparticles also to become photoreactive indoor. And of course, that's the first step in the design process here. As of now, I will call these sulfur-doped titanium dioxide nanoparticles the baseline nanoform. So this is a starting point from where the Safe by Design strategy started within the SbD4Nano project. And actually, within the project, our partner Creative Nano has made surface modifications to the particles by adding silica layers around it, and we will see later in the tool how that manifests. So this is a bit about the context. Of course, what's also very relevant in such a scenario is to have an understanding about the different use scenarios throughout the life cycle, and you can see here some examples where, of course, in the early stages of the product design, you have to synthesize the nanoform. This is a sol gel synthesis for these particular particles. These are then dried and then ball milled, as you can see here in ball milling, and then it's put in an oven where a calcination step is done, and after that it's ball milled again, and then you have here in the bottle you see the actual nanoparticles being shown. These are then put into a formulation and end up in the waterborne paint, and the paint is then applied indoor in the compartment where it has to perform the photocatalytic activity of reducing air pollutants. So this is a bit the contextual background of the case I want to use as an example in the infrastructure. So let's now go to the infrastructure itself. So the infrastructure, as already mentioned earlier, it's an online tool. So at some point you need to ask for credentials once this become available, and you then need to log in. So let me show how that's done. For the logging in step, and then of course just provide a name and a password, and then you get to the point, basically to the landing page of your case. So let's go here, and this is in line with what Carlos was showing earlier, where at the top you have certain groups where members can cooperate together in a group or in cases. And at the bottom you can see the different resources available. And just to give you an impression, here you can see the different resources already presented earlier. So there's a quite extensive list of all different kinds of resources in the community available. You can apply filters on that and to see what potential resource could be become available for your Safe by Design ideas. Another part of the resources is this search for relevant documents. So in this case, I could be, for instance, be interested in titanium dioxide, band gap, and dope. And then we can see what articles and papers are out there. And you can see there's quite a set on that. And you can see here an overview of the most relevant and most recent articles which are related to these terminologies. So that's very handy if you want to get more insight on background information on your products. Another part of the resources available is the resource link to the eNanoMapper database, where you can find a collection of physical-chemical properties and tox and ecotox related data for reference materials, and also materials made available from earlier projects, EU projects. There is a tool in here for the regulatory, to identify the regulatory documents and guidelines which might be of application for your nanoform or for your nano application. And you can also see here, as already mentioned earlier, the different resources in the TNO Diamonds platform, like the e-cards, the exposure quantifier, the hotspot scan, the computational fluid dynamics, and ACell, and the dermal exposure assessment. And we will see later in the assessment itself how we make use of these resources via the API. So let's now go to the actual case. So the starting point of using the infrastructure is basically when you can start a new case, of course, a safe by design case. But of course, for the preparation of this, I already made a case due to limitations of time, of course, we have. And when you enter such a case, you get to this part of basically the landing page of your case. You can provide some background on it, provided a name, and then you can see here the big categories. So you have to introduce the products along your life cycle, the life cycle description itself. Then you can go to the safe by design suggestions, the ranking, and the comparison. There is not a strict order in which you have to follow, so it's more a modeling environment. So you can start with, for instance, describe your life cycle first and then introduce the products as you go. But you can also do it the other way around. And for now, let's have a look at the introduction of products and materials. And you can see here on the left a number of products and materials which are relevant in the life cycle of this case. And you can add as many as you would like. So you can introduce new nanoforms, substances, mixtures, and even articles. And in this case, I introduced some precursors, raw materials used for the synthesis. So you can see here the ethanol, the water, which is actually made by the industrial partner itself, but also intermediate process products, and of course the nanoform itself. So in this case, it's the baseline nanoform. It's the sulfur, the titanium dioxide nanoparticles with the sulfur doping inside. And if you look, you have then to provide some information on to identify it. So provided the name, the type, what is the origin, potentially any descriptors, and then the tool asks you to provide basic information on the nanoform. So what is the composition? You can see the core is made of the titanium dioxide, and the dope is added as sulfur constituent. You can indicate the layout, so which of the constituents are first getting in contact with the surrounding medium. Crystallinity, of course. In this case, it's anatase, the titanium dioxide. The shape of the particle is mainly spheroidal. You can the size information on the primary particle. In this case, it's roughly 11 nanometers, and you can also provide information on the surface area. But as we already saw earlier in the presentation of Mustafa and also in Wouter's presentation, there might already be certain assays conducted for this nanoform, like Phys-Chem characterization. In this case, there is already dustiness measurements has been conducted with the vortex shaker. So that information can also via templates be added to enrich your case. But you can also see here that ecotox data is already added for this nanoform. So here, this is a freshwater algae cyanobacter, but also you can here see an other Daphnia related ecotox test. So all that information can be added if that information is already available for the baseline nanoform. Of course, the nanoform is also to be used in the context of the paint. So you can also add in the products list the paint. In this case, the paint base. I modeled it. It's basically the paint without the nanoform in it, and you can see here the different constituents. So the dispersant, the thickener, the stabilizers, the pigment, and the fillers. And then I combined this paint with the nanoform, and you can see here the composition that the nano-enabled paint is the paint base together with the particles. So there's 5% of the particles put into the paint. So, and this is the way how you can model basically all the different materials and nanoforms in your product, relevant in your case. If you provide information, you can also analyze it at the top. So you can look at the different properties which have been entered, and you can already see I also introduced the safe by design variation, which is the one with the silica layer around it, and also provided all the information on that. And then you can, for instance, look at the plots. And in this case, I looked at the ecotoxicity, compared the original baseline nanoform with the cyanidized nanoform. You can clearly see that the original form is more toxic than the one with the silica layer around it. If you go back to the products overview, you can see here the titanium dioxide, basically the safe by design version, and I also added the TEM page, the TEM image here, and you can clearly see the silica layer around the titanium dioxide, and also these particles are a bit smaller. So basically, what the tool here offers is the ability to add materials, add precursors, introduce articles, and all the relevant products along the life cycle. And you can do that together also with downstream users. The next step would also be to introduce the use scenarios along your life cycle. And of course, that depends a bit on what you're interested in. You can focus on just the manufacturing stage, but you can also consider the use phase or even the end of life if that is relevant for your case. So here you can see I've introduced 4 different use scenarios. So the manufacturing of the baseline nanoform, so without the silica layer. The same, but then with the silica layer, the paint formulation, so the weighing and the mixing of it, and then during the service life when the paint is applied on the wall. And when we now go to the more detail of this use scenario, but because each of the use scenarios has contributing scenarios in it. And if you remember the slide I showed earlier, where you have these different process steps, basically these are represented here. So you can see the sol gel synthesis step, the drying, the ball milling, the weighing, the calcination, and then the second ball milling step. And if we go to the sol gel synthesis, you have to first identify what exactly the step is about. So identify the category of the activity and the task itself. You can provide some background information on it. And then you have to introduce the inputs and the outputs. So basically the mass flow and the materials involved in it. So you can then select just from the materials you introduced in the overview, in the product overview, you can select them there. If they're not in there, you can add them. You can also provide information on the prices. So how much does it cost per volume or per kilogram, which is then later used in the cost calculations. And also you have to relate how much of the input is required to get to the output of this activity. And by linking the different activities within this use scenario, so the outputs of the sol gel synthesis with the drying and the ball milling, etc., then by linking all it, the tool can then at the end, if you go to the output and identify that we want to produce 5 grams of the nanopowder, it can then calculate the amounts of materials involved along the entire life cycle. And in this case, within this use scenario. Let's go to the paint formulation part, because here I introduced two activity steps, which is the weighing. And you can see here a picture of the weighing, which is actually done within the fume hood, and you can see the scooping of the nano powder. And then the second step here is the paint formulation. You can see here this is the lab scale formulation. So they also do it in bigger volumes, and then that's basically in this equipment. But for now, we look at the lab scale. And we are interested in potential exposure and release scenarios here. So for the weighing, you can introduce, and you already saw that, a potential in the picture, that the potential particles might be emitted here. So you can introduce a potential release, and connect that release with the release material form, and also the zone where that release might go into. And in this case, that's the fume hood, which is in that compartment. So let's have a look at the compartments. The tool, besides the use scenario, also allows the introduction of different compartments, like the synthesis lab here. You can see a picture of it. So this is the entire room where the activity takes place. You can see here the fume hood. So you have to provide some dimensions of this room, and you also have to subdivide the room into zones. For instance, the floor is a zone. The far field is the biggest volume of the room where the activities are not happening directly, but also we have the near fields like the fume hood. So there's a small zone here, and also one surrounding the fume hood. And there is one where the ball milling takes place, but that's located behind this desk. So basically, you have to subdivide the compartment into zones where certain activities might release their particles in. And you can see here, so within the fume hood, we have the weighing and the formulation of the paint. Okay, we also can indicate what risk mitigation measures are in place, like this enclosing hoods, the fume cupboard you already saw in the picture here. And the tool can use then the e-card to give some feedback on what kind of controls are potentially available, what the effectiveness is. So this is basically already mentioned by Wouter earlier, but you can then identify if the control selected is actually the one mentioned here. Let's go back. You can also indicate costs and energy consumption involved for this risk mitigating measure. So you can do that for all the other rooms as well, if that's relevant. So there you can see here the room where the furnace oven is located, and also the outside compartment here. So basically, this is the air compartment nearby the vicinity of the building. So let's go back to our use scenario. So that's the paint formulation, the weighing. Like this. So now we have introduced our release and our emission, and the next step is that we can now need to identify what potential hotspots of exposure there are. And as you can see on the picture here in the contributing activity, as you can see in the picture, you can see that there might be potential thermal contact within the fume hood. The hands are located here, but the breathing zone is outside the fume hood. And that's actually modeled by indicating the two different pathways, one the inhalation in the operator zone and the other one in the fume hood. You can also indicate if certain protective equipment is already in place, which ones, and if they are actually applied. And you can do this for all the activities along the life cycle. So once you have done this, and I also did this for the paint formulation, you can see there's also one hotspot here. Then you can go to the overview of the hotspots. And here what you can see is the different activities along the life cycle. And I focus now for this example on potential exposure scenarios and hotspots due to the weighing and paint formulation step. So there might be also here, but I didn't, for this example, didn't identify them. And you can now go to identify the exposures which might occur at this point. So let's click on this, and then we go to the exposure assessment for this this scenario. And here you can see that I used the NEQ model, which was earlier presented by Wouter. And the model basically passes the information I already provided to the NEQ model. So it basically answers these questions the NEQ model needs. And then we can retrieve the results back from the NEQ model. And these are then provided here. And as you saw, there were also PPE used. So then you can account for the PPE effect. And then this is the actual dose, the inhalable dose for this scenario. And you can also do that for the other, for dermal and other inhalation scenarios. Let's go back to the hotspots overview, because here, now you saw how you can provide information. You can also do that by providing measurement data or using other models. But the next step would be that these hotspots introduce safe by design goals. You can see here these pentagons. These are safe by design goals introduced for in these different activities. So for the weighing, we have a safe by design goal, and also for the paint formulation, we have a safe by design goal. But we have also, you can see at the last column, a performance goal, and that's related to the last activity in our use scenario. That's the surface life of the paint, because that's actually when the paint is on the wall, then it has to perform its actual function. So here we make the function operational and say, okay, this is the point in our life cycle where the function matters. Okay, let's go back to the hotspot. So now let's have a look. We have now introduced the SbD goals, but now what kind of safe by design strategies can we apply to reach these goals? So let's click on this pentagon here. And as you can see, for our weighing scenario, the tool creates automatically a so-called influence diagram. And at the farmost right, you can see here the pentagon saying lab worker health is our goal, and we want to maintain it or increase it, improve it. And now you can see, based on the hotspots, that there are two potential risks we should mitigate: the inhalation risk, and here the potentially dermal risk. So let's focus on the inhalation risk. Inhalation risk has two components, as already mentioned earlier. You have the exposure, which you could try to mitigate on the one hand, but you can also try to mitigate the hazard of the nanoform itself. And you can see that the tool has hypotheses, and these hypotheses allow the tool to create automatically causal relationships between these different features as they go along to the right. So you can see here, for the hazard limit, we want to increase that. The higher the hazard limit is, the lower the risk. And we want to do that in relationship to our exposure, which is the route of exposure inhalation. So the lung organ is our targeted subject. Within that, we have certain cell types. We already saw earlier that the cell types, like the macrophages, are the ones relevant in this region. And these macrophage cell lines might be inflicted by oxidative stress, which might be caused by ROS generation, which might be the consequence of the surface chemistry of our original particle. And the tool automatically knows, based on the information we provided, that sulfur and titanium dioxide are ingredients. And as said, as Mustafa already indicated, the sulfur concentration might have an influence of the surface chemistry, might influence the oxidative stress, etc., and cause, in this branch, the hazard. When we focus on the exposure part, we want to mitigate or perhaps reduce the potential uptake. Now, one of the strategies could be to use a filter mask, but as already said, that's the last resort. So we try to mitigate the concentration, basically the exposure of the workers in that room. That can be done by limiting the presence of that worker in the room, and you could optimize your weighing scenario, but you can also try to lower the concentration nearby the fume hood, which you can do by perhaps moving it to a larger room. The dispersion will then lower the concentration as well. You can try to further increase the ventilation rate, but you can also try to mitigate the transport from the fume hood into the near field of that fume hood. And that you can do by try to lower the concentration within the fume hood. And that can be done by enclosure of the weighing, or perhaps try to avoid too drastic scooping of the weighing, so not to put much energy in there. But you could also think of try to lower the dustiness of the particles, which you can do by either modification of the size, by reducing or increasing its aerodynamic diameter, which make the particles settle faster. But another option could be to try to have these particles coagulate faster, so that they will also settle earlier. And that you can do by changing the chemistry or the layout of the particle. But you can also try to influence that by changing the moisture content. And the moisture content of the powder, in this case, you could influence by trying to change the relative humidity inside the fume hood, or you could also try to add a surface modification to your particle, which make them coagulate more fast. This is, of course, from exposure perspective. It's not sure that that's also the best strategy from the product performance strategy. So let's have a look what the tool can, how the tool can use its network to guide the user to potential scenarios. So you can see here an overview extracted from the influence diagram. It says, oh, you could try to increase the particle size a bit, because that might lower the dustiness and as a consequence lower final exposure to the workers. But you could also think of, let's have a look here. Let's have a look if we have a nice one. You can lower the product amount of the weighing. You could increase the automation level. You can, let's have a look if there are other, you can add a hydrophilic group, but as you can see here, the tool also noticed that there might be opposite conflicts, or that there might be a local optimum. So by adding more hydrophilic groups, it might have an opposite effect on another pathway in that influence diagram. And you can see at the far right that it tries to use these conflicts, etc., to give it a first score for this particular goal. Of course, this is from exposure perspective and from hazard perspective, but as I said earlier, we should also consider product performance, and let's have a look at that. So if we go to our hotspots and look at the performance part, then a similar influence diagram is created, but this time the goal is to maintain or increase the performance of our paint. So the photochemical reactivity here, and that's actually provided by the ingredient, which is the nanoform. And there are different pathways which can contribute to this ingredient by perhaps make sure that there's more light available to make it more operational. Make sure that the nanoparticles within the paint are well dispersed so that they are accessible. Look at the performance of the ingredient, the nanoparticle itself, or perhaps the availability of the nanoparticles within the paint. So the amount, the loading within the paint. And here, if you look to the performance of the individual nanoparticle, you can see that photon absorption, if we can promote the photon absorption, it will increase the photocatalytic activity. And we should try to avoid the charge recombination rate, which basically neutralizes the excited state. And this actually, you want to avoid this, and you want to promote this. And then you can see how, for instance, the change in surface area can contribute to higher surface area, will also promote more photons to be absorbed. You can see hypothesis related to the band gap, how a dopant can influence the charge recombination rate, but also the band gap. So here you can also have conflicting scenarios. So if we go to the the potential strategies to increase the performance, you can see that reduction of your size might be an option. And actually, if you remember this, the addition of the silica, actually it produced smaller particles. So by the addition of that silica layer, the particles actually became smaller. You can also think of the loading, put more of the particle in your paint, but that makes it more expensive, of course, and there are other strategies you can follow. So basically, the tool helps the user to think of different potential strategies to follow. Okay, but that now we have seen how the tool can help the user for individual goals. But of course, if you go along your life cycle, you have to take into account all the goals together. So you can see here at the proposed SbD strategy at the top that we have these 3 goals, and now combined, you can see how they all contribute to the overall SbD performance. So in this case, because we have 2 different activities, which both are conducted within the fume hood, so making adjustments or modifications or improvements to the fume hood has a beneficial effect on both the activities, and it doesn't impact the performance of your product. And as you go to the bottom, you can see if you try to change modify the nanoparticles itself, then you might get into conflicting situations that what is good for the performance might have an adverse effect on the exposure. So you can clearly see that the strategies to go for here would be, in this scenario, would be more application of the risk mitigation strategies, local controls, and perhaps also on the activity itself. But of course, if you go along the life cycle, more goals might be introduced, and this matrix might become more complex. And then finally, at the top, we have the comparison tool, and this allows to make comparison configurations. So you can configure different scenarios. So this is, for instance, the baseline scenario. And I also introduced the SbD modification scenario, and I want to look at them from a performance and cost perspective. For the baseline, I selected the manufacturing activities for the baseline, and for our Safe by Design version, I selected the other activities which are used to synthesize the modified version. And then I can go to the compare scenarios, and here we will link to what Wouter was showing earlier. We will go to the performance, and Mustafa already showed that measurements of the performance of the baseline scenario and the SbD modification. You can see here the differences. So there is actually an increase in the performance and a reduction in the hazard. And you can also see here the cost comparison. So this is the baseline, the input materials used, the energy involved, and I didn't enter all the labor costs, but you can provide that information as well. And you can see that the Safe by Design strategy hardly is more expensive than the original baseline. So from a money perspective and time perspective, there is not that much of a difference. So you can use these kind of considerations from tox perspective, exposure perspective, performance and costs to make a decision more in line with the knowledge coming from the tool. Of course, the idea of the tool is to help you reduce the number of trials and errors to get from your baseline scenario to a more safer product. And this basically is a rough overview of the tool. There's of course much more in it, but for now, I hope this gives at least an impression what the infrastructure can offer you as a Safe by Design tool, and to help SMEs and companies to at least increase the speed and the efficiency of Safe by Design processes. And thank you for your attention.